So we were studying fixed axis rotation of rigid objects. Okay, so and what that means is we were studying the rotation of these blades, for instance. Okay, and the rigid, the fact that this was rigid meant that every point on this blade rotated through the same angle. Okay? And so that's why we were looking at rigid objects. And the fixed axis, meaning that the axis, so the axis is pointing this way, and the axis doesn't change directions. Okay? Why were we considering that? Why were we not letting the axis change direction? It's too complicated right now. For $500, we can't consider that, okay? So we were looking at rigid objects rotating about fixed axes, okay? Now, for one-dimensional motion, you guys remember if an object was moving like that, this was the x-axis, and you wanted to describe this motion, describing this motion meant giving x as a function of time, okay? Similarly, describing this rotational motion, so you can think of a general rotational motion. It's turning like that and then goes back and forth like this. Okay, so a general motion is given by, so you could measure the axis, the angle of this guy with respect to an axis, let's say this x-axis. Okay, so that would be the position of the object, and a general motion can be described by giving this as a function of time. Okay, and if you want it, well, okay, so let's say as example, a t square plus bt plus c. Okay, so let's say the angular position of this guy is given by that function of time. So this is a complete description of this rotational motion. Okay, and you saw that to calculate the angular velocity denoted by omega is d theta by dt. Okay, and angular acceleration alpha t is given by d omega by dt. Okay, you saw all this last time. Okay. All right, so again, what we are studying in this chapter is fixed axis rotation of a rigid object. Okay. So for instance, here's an object that is spinning about this axis, an axis perpendicular to the sheet. And, okay, so just like for one-dimensional motion, okay, you chose one direction positive and the other direction was negative. So just like that, for rotational motion, we'll take angles measured from the reference line, we'll take counterclockwise rotation as positive angles, clockwise rotation as negative angles. Okay, just like if you move to the right here is positive coordinates, to the left is negative coordinates. Okay, so rotation counterclockwise are taken as positive angles. All right, there was one more thing we learned last time. Let's say, so again, you're measuring angles from this reference line. So let's say this object rotates like that, and it's come back to that point. Through what angle did it rotate? Again, so I'm starting here and going around, and I've come back here. 360. So what is the angular position? The angular position is 360 degrees. Okay. All right, now I'm going to do the following. Okay, again, start there. I'm going to go around. I'll come back, and I go around and come back. What is my angular position? That's right. Okay, it doesn't reset to 0. Your angular position is 720 degrees or 4 pi radians. Okay? All right, so you have to remember that. All right, so again, even though, so here's the amazing part. even though this rotational motion in no way seemed to be related to linear motion, motion in one dimension. All the equations, corresponding equations are the same, okay? All you have to do is replace x by theta, and you get the corresponding equations, okay? All right, so so here's an object that is rotating about this fixed axis. The axis is perpendicular to the plane, and you use a reference line with reference to which you're measuring angles. And let's say you mark a point on the object, and if the object moves through a distance s, its angular displacement is given by s divided by r. R is the distance from the axis of rotation, okay? And you saw that this is a dimensionless quantity. That is length divided by length. That's a dimensionless quantity, and so it's just a number, but you give it an artificial name, and you call it a radian, okay? So when this is equal to r, and for that, this is about 57 degrees, okay? So 1 radian is about 57 degrees, and you can find this. Pi radians is 180 degrees, okay? So 180 divided by 3.14 is whatever that is 1 radian, okay? So you saw all of that, okay? So now here is this is the initial, so imagine that disk rotating. There's the reference line, there's the initial position of the disk, and there's the final angular position of the disk. So initial angular position and final angular position. Okay, so the angular displacement is defined as theta final minus theta initial. This is just like in one dimension. Here's the initial position, here's the final position, okay? And this is the displacement. Delta x is x final minus x initial, okay? So the parallel of that is angular displacement, okay? Average angular speed, okay, will come with the direction in a bit. Anyway, angular speed is delta theta by delta t, okay? So, yeah, so actually this is magnitude of angular velocity. So angular velocity is displacement over time, okay? And instantaneous angular velocity would be, so we call it speed because it's a magnitude, but instantaneous angular velocity is d theta by dt. Get time derivative of that, and we'll give you the direction of the angular velocity in a second, okay? So here's the direction of the angular velocity. So if you have an object that's rotating this way, and remember our axis is fixed, so this cannot shift. And so the only two ways the object can rotate is either this way or that way. This way or that way. Okay, so if you're looking down like this, this is counterclockwise rotation, and this is clockwise rotation. And the direction of your velocity is given by your right-hand rule, okay? Your fingers point in the direction of the spin, and your thumb points in the direction of the velocity, okay? So your velocity points along the axis. It can either point this way or that way. And you take this to be positive and that to be negative, okay? All right, so that's how you figure out the velocity, okay? Yeah. So when do you have linear acceleration? Acceleration is when velocity changes with time, okay? So that's what you learned for linear motion, okay? And so we'll extend that concept for angular motion, okay? So when angular velocity changes, then you have angular acceleration. Angular acceleration is denoted by alpha, and this is omega. So if the angular velocity did not change, this would be 0, and your angular acceleration would be 0, okay? So you have non-zero acceleration only when your velocity, angular velocity changes, okay? And angular acceleration is rate of change of angular velocity. So if your velocity changes by a large amount in the same time, you have a larger acceleration, yep. Of course, you guys are all calculus experts, so angular acceleration is d omega by dt, yep. So angular acceleration is d omega by dt, and but d omega was d theta by dt. So angular acceleration is d squared theta by dt squared. All right, so going back to that example, so let's say, so you have this disk that is rotating about this axis, let's say, and you're measuring the angular position of this guy with reference to this line, okay. So if you give its angular position as a function of time, 5t squared plus 7t plus 10, okay, its angular velocity will be 10t plus 7, and angular acceleration will be d omega by dt, d squared theta by dt squared. Okay. And this would be radians per second squared. That would be the SI units. Radians per second and radians. Okay. All right, so you'd seen this before. When the position is a quadratic function of time, acceleration is constant. Okay, so you saw that. When position is a quadratic function of time, velocity is a linear function of time, and acceleration is constant. Okay, so if you want a complete, if you ask somebody to describe this angular motion completely, it could be doing anything. What they're asking you is give the angular position as a function of time. If somebody gives you that, they have given you a complete description of the motion. Okay? And from this, you can calculate stuff that you're interested in calculating. Okay? Now, most of the time, we are satisfied with this thing. Okay? Sometimes, so if you ever have to calculate the rate of change of acceleration, then you're in a good job. Okay? So let's all hope that you'll all get there. Okay? And this is called a jerk. Okay? It really is called a jerk. All right, so we saw all of this last time. Okay? Well, this and more. Okay. Now, you guys remember in for one-dimensional motion, if velocity was in this direction and acceleration was in this direction, what is happening? What is happening to the speed of the car? It's increasing. Okay. And if the velocity was like that and the acceleration was like this, the speed of the car is decreasing. Okay? The magnitude of the velocity is decreasing. Same thing with angular motion. So if an object is spinning like this, again, use your right hand, point your fingers in this direction, the velocity is pointing in that direction. And if the acceleration points in that direction, the angular speed is increasing. If if the velocity is pointing this way and the acceleration is pointing that way, the speed is decreasing. Okay? So for instance, in your car, if you're driving your car this way, okay, if your car is moving this way, the angular velocity, the wheels are spinning this way, so your velocity is pointing in that direction. Angular velocity is pointing perpendicular to the direction of motion. Okay? And if you're accelerating, the acceleration is pointing in that direction. And if you're applying brakes, then the acceleration is pointing in that direction. Did you guys understand that? Okay. Question? Okay. All right, so again, like I said, even though these two motions look very different, a lot of what we learned here applies to this situation as well. Okay? Okay, this is something, all right, so this actually only applies for infinitesimal quantities And even though this diagram does, so this should be for d theta. So what this diagram is telling you is, okay, so here's an object, let's say, which is spinning in this direction about that axis, okay? And when it rotates, when this object rotates through a small angle d theta, the displacement vector is in this direction. This is the small distance, this is the infinitesimal distance that this point moves from here to there. Okay, that's what this is giving you. Again, it's giving you as a cross product. This is a vector, displacement vector. R is the vector of this point from the axis of rotation. Okay. Again, don't worry about that. We won't be using that too much. This also is doing the same thing. This is that's the angular velocity of the object rotating, and this gives you the linear velocity of this point that is at a distance r, that's at location r from the axis of rotation. Okay. Again, we won't worry about that. Okay. This is giving you the tangential acceleration. So what this is giving you is the following. So again, here's an object, and if this has angular acceleration, what does that mean? This thing is spinning faster and faster. And if this thing is, its angular speed is increasing, the linear speed of this also is increasing. The speed is increasing. And when the magnitude of the velocity increases, you have tangential acceleration, and that's what this is giving you. Okay? The rate of change of speed of this guy. Yep. All right, so for linear motion, when A was constant, okay, when the acceleration of the object was constant, we had these equations, okay. For constant acceleration, the final velocity of the object, so okay, so when an object was moving in a straight line at constant acceleration, the initial velocity, initial position, and final velocity, final positions were related, and they were given by these formulas. Final velocity was equal to initial velocity plus acceleration times time. Final position was equal to initial position plus initial velocity times time plus 1/2 AT time t squared. So there was the position as a function of time, velocity as a function of displacement, or velocity as a function of position. So how fast was it going at this location, and so on. Okay. These equations are called the kinematic equations that were valid when A was constant. And we're going to derive exactly similar equations for rotational motion for constant angular acceleration. Yep.
And with these, when you solve for the angle, you said you get them in radians?
Right. Well, in these formulas, yeah, you could.
Would we ever have to convert them into degrees?
Here in these formulas, you can use radians or degrees or revolutions for these formulas. The only time you have to use radians is when you're relating linear quantities to angular quantities.
Would we ever have to do that?
Do what? Oh, you're doing this all the time. You'll be doing this all the time. So for these three formulae, you have to use radians. Okay? You absolutely have to use radians. Okay? So again, whenever you can relating linear quantities to angular quantities, the units have to be radians. Okay? Here you can use anything you want. Degrees, revolutions, degrees, radians, and whatnot. Okay. But again, so what we are doing now is, in the next few slides, is, see, for linear motion, when acceleration was constant, and you had initial velocity and initial position, and this was the final velocity and final position. you had formulae that related these to these guys, okay? Or these guys could be calculated in terms of these guys, and that's what these formulae are. Final velocity, initial velocity plus a times t, okay? Velocity is a function of time. How fast are you going after this elapsed time? Where are you after this elapsed time? How fast are you going after having traveled this distance, okay? So here are the corresponding formulae, okay? And again, you can get these formulae from these. All you have to do is the following replacement. X gets replaced by theta, V gets replaced by omega, A gets replaced by alpha. That's it. Okay, that's the prescription. And the formulae are exactly the same. Okay? So what is this formula saying? Okay, if this guy is rotating and he's accelerating, meaning he's getting faster and faster or slowing down, the final angular velocity is initial angular velocity plus alpha times time. Okay? So angular velocity as a function of time. Okay. What is this formula telling you? Again, this thing is rotating, and if he has a non-zero acceleration, this is the final angular position as a function of time. Okay. So, and in these formulae, again, the angle doesn't reset. It goes 360 degrees, 720, and so on. Okay, this thing is a continuous parameter. It doesn't reset at 360 degrees. Okay, so you have to remember that. And this is initial angular velocity and angular acceleration. So again, this is angular displacement. This is average angular velocity, okay, times time. So again, you saw all of this. Okay, so the kinematic equation for motion in one dimension at constant acceleration. These are kinematic equation for rotational motion. For what kind of objects? Does this, huh?
Fixed axis bodies with that are solid, they won't move.
Rigid objects about fixed axis rotation. So will this apply for a cup of coffee? If you stir a cup of coffee? No, it doesn't apply to that. Why is that? Because all parts of the coffee are not rotating through the same angle. Okay? Coffee close to the surface of the cup is rotating through lesser angles. All right, so here are some formulae that relate linear quantities to angular quantities. Okay, this is the linear speed of a point that is r. R from where? From the axis of rotation. Okay, so if this object is rotating and here's the axis of rotation. So what this formula is giving you is the speed of this point. Okay, of this point that is r distance away from the axis of rotation. Okay, times the angular speed. So all points on a given radius, so all points of the wheel are going at the same speed. Okay? All right, for a rotating wheel. So the further out you are, the greater the speed. Okay. And this is, see, in your car your car engine is able to provide a maximum angular velocity. Okay? So is there a way to make your car go faster? Your wheel is only able to provide a maximum angular velocity. So that's why you put bigger wheels. If you put bigger wheels, you can have a greater maximum speed for your car. Okay? That's why people put bigger wheels. All right. Now again, we saw all of this last time. Okay, so here's an object that's spinning like that, and again, where is the axis of rotation? There's the axis of rotation, and it's perpendicular to the plane. Okay, And if it has angular acceleration, then the speed of this guy is increasing, so he has tangential acceleration. Okay. Now, if you take a snapshot of his velocity is pointing in this direction. Okay. In a little while, his velocity will be pointing in this direction. You guys understand? Okay, so the magnitude of the velocity is changing. And because the magnitude of the velocity is changing, he has tangential acceleration. Tangential acceleration is when your speed is changing. The direction of the velocity is also changing, and so you have radial acceleration, or we also call it centripetal acceleration. Okay? So if this guy has angular acceleration, then this guy will have tangential acceleration and centripetal acceleration, and that'll be his total acceleration. Okay? Now, how do you provide centripetal acceleration? All this stuff is holding on to it. Okay? So if your car tires are dirty, okay, if you have sand on your car tires, if you accelerate super fast or you're going super fast, then all the dust will fly off. Okay? So that's one way to clean your tires. Drive super fast. Yeah. All right, again, tangential acceleration is the rate at which the speed of this point is changing, and tangential acceleration is r times alpha. What are the units for alpha again here? Revolutions per second square, degrees per second. Okay, this is relating linear quantity to angular quantity. So in this case, this is always radians per second square. Okay, this has to be in radians per second square. All right, centripetal acceleration is the acceleration because of change in direction of the velocity, and that's equal to v squared by r, and that's equal to r omega squared. Okay, when do you have kinetic energy? When you're moving, that's when you have kinetic energy. Okay, so here's an axis of rotation, and there is this object rotating like that. And you saw that the speed of any given point is given by v equal to r omega. Okay, so the further out you are from the axis of rotation, omega is the same for every point on the object. So the further out you are, the greater your speed. Okay. So the kinetic energy of this whole object is the kinetic energy of this point plus the kinetic energy of that point, and so on. Okay. So again, you saw that the further out you are, the faster you're moving. So this guy is moving in this direction, this guy is moving in this direction. Okay. And the further out you are, the faster you're moving. So the kinetic energy of this whole object is the kinetic energy of this piece plus this piece plus this piece, and so on. And that's what this is. This is the kinetic energy of each little piece. Okay? And then you're summing over all the pieces. Okay. Yeah, go ahead. All right. So you're summing over all the pieces, and each velocity is written like so. Okay. Each velocity is written like so, and you square that, and you see omega is the same for each piece. So you can pull omega out, omega square out, and this quantity is called the moment of inertia. Okay. So you see moment of inertia is each piece. See, the moment of inertia of this object is the mass of each piece times the distance of that piece from the axis of rotation. So you can see that the moment of inertia for an object can change if you redistribute the pieces. If you make the pieces come closer with the same total mass, the moment of inertia will be smaller. So the closer the mass is distributed to the axis of rotation, the smaller the moment of inertia. If all of them is right, all of the mass is right on the axis of rotation, then the moment of inertia will be very small or zero. Yep.
I understand when you use that equation.
Mm-hmm.
I understand that. this with two sticks with two separate masses.
Mhm.
I see that we'd use those two masses, but what if, like, it was a solid disc?
Mhm.
How would you add up those masses?
So you would do an integral, and here is the moment of inertia for a disk. So, so you could, here. So here's a cylinder for a moment of inertia about that axis going through the center is 1/2 mr squared. Okay. Somebody has done this integral for you. Yeah. Okay, so the mass of an object doesn't change, but its moment of inertia changes depending on how the mass is distributed about the axis of rotation. So for instance, you've seen ice skaters speed up by bringing their arms in. What they've done is, you'll see in the next chapter. Okay, anybody remember the formula for linear momentum? Mass times velocity. Okay? So we will define something called angular momentum next chapter, which is I times omega. Mass gets replaced by I, and V gets replaced by omega. Okay? So now you'll understand something. So if there's a mass distributed about the axis of rotation, if you bring it closer, I can be reduced. So when an ice skater spins and he or she brings their arms in, they're reducing R for some mass, they're reducing I, and this quantity remains constant so that their speed increases. So that's what they're doing. Okay? And we'll see these examples next chapter. Okay? So the moment of inertia of an object depends on the mass of the object and depends on how the mass is distributed about the axis of rotation. Okay? A given object can have only a single mass, but an infinite number of moments of inertia. Okay? Depending on how the mass is distributed about the axis of rotation. So here's a simple example. So for this object, if you calculate the moment of inertia about this axis, these guys are right on the axis, so they don't contribute any to moment of inertia, but these guys do, and the moment of inertia, that is that. Okay. The moment of inertia of the same object about this axis, about an axis passing through there perpendicular to the plane, is that. See, this moment of inertia is greater than that. Okay. So for instance, I mean, this kind of stuff is real, so in the sense that, okay, so this room is full of diatomic gases, so, and these molecules can rotate. Okay, so the rotation about this axis is possible, and the rotation about that axis is possible. Okay, so let's say this is the y-axis, this is the x-axis, but a rotation about this axis is not possible. Okay? So for all these diatomic molecules in this room, which are nitrogen and oxygen, they can rotate about that axis and that axis. They have 2 degrees of freedom, and you'll learn about this later. But they cannot rotate about this axis because the energies involved, I is close to 0, and energies involved in that thing are too high. Okay? Anyway, you'll study this. We'll look at this later. Okay. So here's what I want you to remember. The mass of an object is a single number, and that doesn't change. But the moment of inertia, an object can have an infinite number of moments of inertia depending on what axis you're calculating it about. And the moment of inertia of an object can change. Okay? All right. So you guys have all seen this. So all I'm doing is changing my moment of inertia. And what is constant is, and you'll see this, what through the entire motion, if there was no friction, the angular momentum was remaining constant. I was decreasing, when I was decreasing my moment of inertia, angular velocity increased, and when you increase the moment of inertia, angular velocity decreases. Okay? So that's what was happening there. Again, moment of inertia are important quantities. Okay? And for a continuous object, for a continuous distribution, you calculate the moment of inertia like so. Okay, so for point objects, moment of inertia was like calculated like so. Okay, so we are going to generalize this to an integral. The summation is going to be replaced by the integral. There is the r square, and that's the mass of that little piece. Okay, so you break this up into little pieces and do this integral. And again, this is a three-dimensional integral. Okay. The mass is density times volume. Okay, and so here's what the integral will look like: dx, dy, dz. So that's a three-dimensional integral that you'll be doing. Okay, and of course, most of them, for regular objects, they're kind enough to do that for you, and you will have tables like this all over the place. Okay? So these quantities are useful. So moment of inertias. Okay? Most of these tables give you the moment of inertia of a uniform object about an axis passing through the center of mass of the object. Okay? So you might have, the table will give you the moment of inertia of an object about an axis passing through the center of mass. Sometimes you'll need the moment of inertia of the object about an axis that doesn't go through the center of mass. Then you can use the parallel axis theorem. So the moment of inertia about this axis is equal to the moment of inertia about this axis plus the mass of the object times this distance squared. Okay? And that's the parallel axis theorem. Okay? There's the mass of this object. Okay, so if I want to give an object an acceleration, what do I have to do to it? How do I give an object an acceleration? So to give an object an acceleration, you have to apply a force on it. Okay? So if you apply a non-zero force, you can give an object an acceleration. So now what we'll learn is, if I want to give an object an angular acceleration, what you have to do is apply a torque to it. Okay? Torques will give objects an angular acceleration. Okay? And so now we'll learn about torques. Okay, so let's say here's an object, and it's fixed to rotate about that axis. Okay, and so here's the axis of rotation. Okay, and now if you want to turn this, you guys all know that if you apply a force like this, it'll make the object rotate like that. You also know the following. Okay, let's say I apply the same force, but I'll apply the force in this direction. Okay, so I'll apply this same force. So let's say I apply 10 pounds in this direction, I apply 10 pounds in this direction. Will it rotate with the same acceleration? No. Okay. Which will be greater? This one or this one? The first one will give an greater angular acceleration. So you already know, intuitively know that the magnitude of the force is the same, but this guy gives a greater acceleration, so that guy must have a greater torque. Okay, the same magnitude force, this has a smaller torque. okay? So it turns out that the torque depends on the magnitude of the force and the point of application of the force and the direction of the force, okay? All right, so a given force has a torque to it, okay? And what is the torque of a given force? We'll give you that in a second, okay? So this is a vector equation, okay? So the torque of a force, okay? The torque of a force is given by this R cross F, the cross product. R is the vector from the axis of rotation to the point of application of the force, okay? So this cross product is the torque, okay? And that will give you, so if this force were pointing in this direction, that will give you a smaller magnitude torque. If it was pointing in that direction, that will give you a greater magnitude torque, okay? So now you guys understand the following fact, okay? Door knobs are put on doors always on the end. They don't put doorknobs here in the middle, right? Why not? What's that? I'm sorry? No, silly is a relative term. I'm sorry? Why? So here's the deal. So torque is, so in this case, torque is this perpendicular distance, this distance, the distance from the axis of rotation times the magnitude of the force, okay? This guy is called the moment arm, okay? If you put the doorknob there, the moment arm would be half, the torque would be half as much, the moment of inertia of the door is the same. If you apply half as much torque, the acceleration is half as much, and it's taking forever to open the door, okay? So, and also, if you put the doorknob right there, right on the axis, this will be zero, torque would be zero, this would be zero, you'll never open the door, okay? So even Superman couldn't open the door if you put a doorknob right there. Yeah. Of course, Superman will be able to pull the door off the hinges, but that's a different story. Okay, so the torque of a force is R cross F. Okay. So here's an object, there's the axis of rotation, and if you apply a force like that, there's R cross F. Now let's say I apply a force at this point in this direction. Can I open the door? Or can I rotate the object? Why not?
There's no tangential force.
Yeah, so when R and F are parallel to each other, the cross product is zero. The torque is zero, okay? And you won't be able to give any angular acceleration. Similarly, if I applied a force in this direction, R cross F is zero, okay? R cross F is maximum. You guys all know this intuitively because you've used a wrench. And what, for a given force, in what direction will, when you apply the force, in what direction will you get maximum torque? If you apply the force in this direction, when R and F are perpendicular to each other, that's when the torque will be maximum, okay? So the magnitude of the torque is RF sine phi, where this is R and there is the phi. Okay, so this will be max when this guy is 90 degrees. Okay, when this guy is 90 degrees. So this, for this guy, that's 90. That angle is 90 degrees and the torque will be maximum. Okay. Do you guys remember Newton's second law? What's Newton's second law?
With respect
I'm sorry?
to force equals mass times acceleration.
Yeah, force equals mass times acceleration. Now, is this the general formula?
Special case.
Okay, what is the special case?
Mass is constant.
When mass is constant, okay? So when mass is constant, the general formula is F is dP by dt. P is, of course, m times v, so dm by dt times v plus m times dv by dt. Okay, so when the mass of an object doesn't change, then this reduces to that. Okay, so that's the special case. So similarly, so the parallel of this for rotational motion, okay, so forces give linear acceleration, torques give angular acceleration. So here's the general formula. So dl by dt, and L is, again, L will introduce next chapter, but it's angular momentum, just like linear momentum. The parallel of linear momentum is angular momentum, and this is dl by dt, okay, which is di by dt times omega plus I times d omega by dt, okay. Now, in situations where moment of inertia does not change, this will be 0, and torque will be equal to I alpha. So here is the special case. So here's Newton's second law. This should be torque. Okay, that's torque. Torque is I times alpha. Okay, so here's this Newton's second law for rotational motion. Torques give angular acceleration. Okay. And that's what this derivation is showing you. I mean, this diagram is showing you. So imagine, imagine a mass attached by a thread to this point, and it's going around like that. And if you apply, or this could be a merry-go-round, and this is a chair, and you're pushing on this chair, okay, and you give it an linear acceleration. Okay, the torque of this force would be that force times this distance. And that's what this is. The torque is F times this distance. And you're giving it a linear acceleration. Anyway, it goes through all the derivation and shows you that the torque is equal to I times alpha for this point particle. Okay. But this formula can be generalized. When is this true again? When is this true? That's right. Very good. When this guy is constant. Okay. So whenever you're talking about a rigid object rotating about a fixed axis, then this is true. But when the object is not rigid and when this changes, so you have to add this term. Okay, so when I was sitting on the chair and spinning and changing my moment of inertia, I have to use this formula. I can't use this formula. Okay. All right. So again, for a rigid object rotating, the net torque is I times alpha. Okay? So this is when this guy is constant. All right, so if you check your notes, let's say this car is moving like that, and you're pushing on the car. Okay, the power is, so if you're pushing on the car in this direction, let's say, the power or the rate at which you're doing work is F dot velocity. Okay? Similarly, if something is rotating, so for instance, if this is rotating and you keep, so I showed you that wheel, and I kept pushing on the rim of the wheel. So if you keep applying force, the power, the rate at which you're working is the torque times omega. Okay. So the rate at which your car is working, for instance, car engine is working, is the torque it's applying times the angular speed of the wheels, or the angular speed of the shaft. Okay, that's the rate at which your car is providing, the rate at which your car is working. Okay. for linear motion, if you had several forces acting, so if you had several forces acting on the object, and if these were the only forces acting, the net work done by all these forces shows up as change in kinetic energy. You saw this, that was the work energy theorem. The net work done was equal to final kinetic energy minus initial kinetic energy. Okay. So these guys were affecting linear motion of the object. So if you apply bunch of forces that are affecting the rotational motion, only the rotational motion, so these forces have torques. So this weight is trying to rotate this object clockwise. This guy is trying to rotate him counterclockwise. So if you have several forces acting, the work done by all the torques shows up as change in rotational kinetic energy. Okay. So this is final rotational kinetic energy, initial kinetic energy. So the net work done by all these torques is that. So there's the work energy theorem for linear motion. There's the work energy theorem for rotational motion. Okay. So you studied all these formulae in 9 chapters. This is all these formulae are for linear motion. All that 9 chapters condensed in 1 chapter here. Okay. Well, actually, in this and the next chapter. Okay. So every formula that you studied for linear motion, there is a corresponding formula for rotational motion. Okay. And all you have to do is, for linear motion, if x gets replaced by theta, b gets replaced by omega, a gets replaced by alpha, mass gets replaced by moment of inertia, linear momentum gets replaced by angular momentum, force gets replaced by torque, okay, and so on. Okay, so you replace these variables by these variables, and you can go from here to there. Okay, so here, v is omega, x is theta. Okay, so v is dx by dt, omega is d theta by dt. Okay. A is dv by dt, alpha is d omega by dt. Okay. F equal to ma, torque equal to I times alpha. And here are the kinematic equations and so on. Okay. Power is F times V, F gets replaced by torque, V gets replaced by omega. Power is that. Okay. Linear kinetic energy is 1/2 mv square, 1/2 I omega square. Again, you replace these variables. You replace these variables by those variables, and you go from linear to rotational motion. Okay. So it's exactly the same formula. Okay. So again, here's a very amazing fact. I want to explicitly state it again. Okay. An object moving in 1 dimension, this motion is very similar to a rigid object rotating about a fixed axis. They look so different, but mathematically they're equivalent. Did you guys understand that? The location of this guy is given like so. The configuration of this guy is given by that. Okay? And the two motions are identical. Okay? They're mathematically equivalent. That's the amazing part. Okay? So this is mathematics, and this is physics. All right. All right. So here's just a neat little application. Okay. So you guys have used these devices. These devices store information on that line. and the information is stored as like so. The information is stored in binary digits, okay? So this could be zeros and that's 1, okay? So information is stored as 0, 0, 1, 1, 0, 1, and so on. And that's what's written here on this thing, okay? And the way you read this is the following. You shine light on it, and when the light hits a bump, the light gets scattered, and here's a detector, and the detector doesn't get back anything. When the light hits this thing, the flat area, you get a lot of reflection to the detector, and you get a signal, okay? So that's how you read the bumps and flat areas. Now here's the deal, okay? So the light is a laser beam, okay? Now, this is the wavelength of the laser. This is the wavelength of the light, crest to crest distance denoted by lambda. Okay, if you use this wavelength, the smallest object you can read is this big. Did you guys understand that? Okay, so what if you want to read a smaller object? What do you have to do? So you have to use a shorter wavelength light. This is red light, this is blue light. So now you can read a shorter object. Okay. What's the advantage? You can store more information. You can put these lines closer, and you can put these bumps closer. Okay, so this was regular CDs, this is the Blu-rays, and so on. Okay, what's that?
I was just about to ask if that's what Blu-ray was.
Right. So regular CDs used red light, and the spacing had to be 1.6 micrometers between the lines. Okay. So with Blu-rays with a shorter wavelength, now the lines can be 0.3 micrometer, 5 times closer. In addition, those bumps could be 5 times closer. So the information content should be 25 times as much. So so in the same area, see, 5, the track length was at, okay, the information content should be 25 times greater, 1 gigabyte to 25 gigabytes. So when you went from this longer wavelength to blue wavelength, the information content was 25 times greater. Now here's another interesting technology. You guys understanding this? So here's another interesting fact. So what you do is you're shining the laser right there, okay, and the laser moves outwards as you're reading. But you know, the laser is sitting at a fixed location, and it's just moving radially outwards. So as you're reading, this line has to move at constant rate. So the speed of this has to be constant, okay? This has to be constant, and as you're moving outward, as you're reading further and further lines, this is increasing, so the angular speed has to decrease. Okay, so this V is R omega. So the angular speed of this disk is variable. So you have to have a variable speed motor, and its speed has got to change at a constant rate. All right, guys, so that covers this chapter.